Hey guys, Eric McGray here from Avant Manufacturing. I'm here with another video, and in this one I want to talk more about tool holding. So basically, when I did the last video and when I tested the prototype heat shrink holder from Tool, my idea was basically first things first, I want to see if the tool will stay in the tool holder. Because in my experience, so far, the weakest link in the tool holder chain for me has been just holding onto the tool, making sure it stays where it's supposed to be. And by that I mean pulling out of the tool holder has been an issue when I try to push various operations. So that was the first thing I wanted to test. And this video is about the things I learned when asking questions about how tools are held, and what makes one tool holder hold a tool differently, or hold it better or worse than another. So, and a lot of the quantitative values that go with that kind of thing. So, really try to dig down a little bit into the engineering and the physics behind the tool holding. And so, it has a lot to do with, forces and mechanical properties of different materials and things like that. So without further ado, let's talk about it. Again, so forces, basically number one thing is forces. Like, as a machinist, you know that you deal with forces all the time. That is what we do. Using force to create a shearing action and removing material from a stock to sculpt a part, that is in essence what machining is. So, and that force that you use to do that gets distributed in all different kinds of ways. So, it accelerates the chip leaving the stock and causes it to, move faster than it was before you decided to remove it. That force can cause tool deflection. It can cause vibration. So those forces, it gets that force also, the friction that is, when you take that force and you plow that tool into a material, the friction between the two, that force then turns into heat energy. So the force goes many different ways. Now, thinking along those lines, you want to ask yourself, or maybe you don't, but I did, and I do, what is causing my tool to pull out when I try to rough aggressively? Well, so milling cutters and mills, first thing I thought was, well, they've got a helix angle. Now, you take that rotational force, that torque, and you begin removing chips from the material, or swarf, blokes out there or something. So you have a helix angle, and so that angle, it's essentially a wedge that is wrapped around a cylinder. That sounds kind of familiar, doesn't it? A screw, something like that. So basically that helix angle acts similarly to a screw in that it takes rotational force and it translates some of that into force along the tool's axis. And that force along the tool's axis happens to be one where the tool it's acting on the tool, trying to pull it out of the holder, at the same time trying to pull the material out of your vise or whatever work holding situation you might have. So, and to the degree that helix, or we should call it, what do I want to call it? What is the term for it actually? How fast? That's what machinists call it, right? How fast that helix angle is. So if you've got it's got a fast angle. Skip that part of it. I'm going to talk about helix angle in terms of degrees, because that's the way that I think about it. So typical aluminum finishing end mills tend to have like a 45-degree helix angle. So that means there's a 45-degree ramp which wraps around the tool, and that is the flute. The cutting edge is at that 45-degree angle, right? I use tools actually that are 37 or 38 degrees. I can't remember, one of those. So that would be a faster helix angle than the 45. So slower helix angle would be like 60, something like that. So anyway, you think about a faster helix angle, or one with, and this angle is measured from the tool's axis. So you think about a lower degree or a faster angle, and it will actually, with the same cutting parameters, you compare, 37 degree versus a 45 degree, the 45 degree is going to take more of that force and translate it into axial force. And so trying to rough hard with a tool that has a slower helix angle will more likely cause the tool to be pulled out if there is no positive lock. Before I get to positive locks, let's talk about just collet type systems, right? Collet type systems, heat shrink holders, what else is there that, drawing a blank. But anyway, any type of system that just, press fits, any type of system that just grabs on the cylinder of the tool with no other locking mechanism. No flat, no whistle notch, no safe lock grooves, none of this. Just straight up grabbing on the cylindrical surface of the tool shank. So when I think about this, I think, okay, well, say we can calculate the axial force that goes into the tool, right? Attempting to pull it out of the holder. And assuming that we calculate this because if we know our cutting parameters, if we know material properties, their formulas have already been established for calculating these kind of forces. So you can look them up. I would totally just post them up here and maybe even do like screenshots of Excel spreadsheets and things like that. Not too good with the video editing yet. Just gonna sit here and lecture because that's really easy for me to do. So I don't want to spend too much time editing. I'm sorry, being lazy, trying to take some time away from machining right now. Not really, it's running in the background. Anyhow, and I don't want to, anyhow. So I'm not gonna do that. You can look up these formulas yourself. Maybe I'll throw a link in the description, something like that. That I can do. So back on track. We can calculate the cutting force of the cut that we want to take. We describe our tool, we describe our material, and using these formulas, we can basically predict the cutting force that there will be, the amount of torque on the tool, and then helix, and you can figure out the axial force. So, okay, now we're at this point. Say we know the axial force attempting to pull the tool out of the holder. In the heat shrink holder example, because I tested that and I made a short video of just running it at some high speeds, I'm using that as an example. I wanted to know why the tool didn't get pulled out, right? And I wanted to know also, when would it get pulled out? Like at what cutting parameters would it get pulled out? And I just wanted to know in order for me to kind of give myself like a safety barrier, right? I don't want a tool to get pulled out. So I want to know when it would possibly get pulled out so that way I can try and reach my limit rather than, if I don't want to just machine way below the limit. If the limit is all the way up here and I'm machining way down here, I want to machine not at the limit, I want to machine just below that. I want to machine right where it's safe enough, but where I'm also being very productive. And maybe you do too. So that's why you're watching this video. Hopefully you'll learn and can make some use of this stuff. So, okay, so we know the axial force trying to pull the tool out of the holder. What's next? what is next? What is holding the tool in there? Okay, well, basically, if we're talking about an ER collet, we've got radial clamping force because that collet, basically when you set up a tool, you apply a torque to the collet nut, okay? So that torque, basically, because of the threads, the screw threads there, that torque gets translated into axial force, similarly to how just the torque on a cutting tool and its helix angle also translates to axial force. So you can take that torque and you can basically estimate the force, the axial force that's being put into the collet. And then with that collet, now you have a taper angle on that collet. And that taper angle translates that axial force into the radial compressive force that grabs onto the cylindrical shank. Okay, so now we have a force grabbing the shank, and in the case of a heat shrink holder, basically you have a force grabbing on the shank because it's an interference fit. And that's a little different. In order to know what that force is going to be, you have to know it's leaving my head right now. Drawing a blank. You have to know the coefficient of thermal expansion. No. I forget right now. So I don't have any materials here to remind me. I didn't prepare for any of this. I'm just going off the top of my head and all this studying stuff done. I forget when it was. I don't keep track of time too well. So anyway, I figured out, I calculated how heat shrink holders, how much clamp force they would have on a given tool based on the material of the holder and one of the mechanical properties of it, and also the size of the interference, and yes, basically something like that. I think there might have been one more value that had to be worked in somewhere along the way. But anyway, let's go back to the ER collet example, because that one's simpler. Because we can just think in terms of forces: the torque, the axial, the wedge cone, yeah, and compressive radial. So what's next? So on this side we have our cutting force and helix angle and fun stuff, and translating that into an axial force. So that's trying to pull the tool out. Now on this side we figured out what leads up to the radial compressive force on the tool shank. Now between these two, basically it's coefficient of friction, right? I mean, if you have no positive lock on your tool, like the Heimer safe lock grooves, or just weld them flat, something like that, it's just friction that holds it in. It's purely friction, right? So that's the part of the equation you got to find out. And so I basically just looked up online, carbide, tungsten carbide, coefficient of friction on steel. There wasn't anything specific, any specific alloys or something like that. If I wanted to do a more precise test, you can totally just take a piece of carbide and the piece of the type of steel, the H13 steel or something like that, and take like an old end mill and shank, do the whole coefficient of friction test where you put the weight on, you got you pull it, yeah, something like that. So, and you can measure coefficient of friction yourself. It's really simple. It's a really simple, easy thing to do. I might do it sometime. I don't know if I want to get in that deep. I may, but anyway, what I learned from doing all this fun stuff and creating spreadsheets and formulas and all that stuff, and once I put that coefficient of friction between tungsten carbide and steel, in general steel, into the calculation, I was a bit surprised, because I was doing all this for the purpose of figuring out how much clamping force the heat shrink holders in general, not just Maritool, but heat shrink holders in general. Most of them are made of that H13 tool steel. Some have, Heimer, Tautz they develop the material with the manufacturer of the material, the mill and such. So they, especially for their heat shrink holders and all that. So, but anyway, in general, I just wanted to understand what kind of clamping forces are holding onto the cutting tool, and so that way I could know how hard I could push a tool without pulling it out. And I was very, very surprised actually. And what I found was that, again, just remembering off the top of my head, I'm not going to say any numbers because I'm just going to embarrass myself because they're probably going to be wrong. I'm just going to make them up and it's not good. So anyway, I just learned that my machine will not be able to pull a tool out of the holder, a 1/2 inch 3-flute 37-degree finishing end mill out of a heat shrink holder, a typical heat shrink holder. Just won't, as hard as I want to push it. The machine just doesn't have the power to do it. The power at 15,000 RPMs. Generally, I run 15,000 RPMs in aluminum. So, this is another part that I want to talk about. I know the video has gone on long enough already, but I hope you're learning something and you're sticking by, or even if you didn't learn too much just yet, it gets some wheels turning and you start thinking about these kind of things. Because I find it really interesting. So, I won't be able to pull out a 1/2 inch tool on my machine at 15,000 RPMs. And the reason is because the machine doesn't have the power to do it. Now, power is a function of torque and speed, rotational speed. So at 15,000 RPMs, the max power, we already have a high speed at 15,000 RPMs. So to get a max power and you divide a speed, you basically the amount of torque times 15,000 RPMs that would equal the max power is less torque than if you were trying to achieve that same amount of power at a slower speed. So is it possible that I could pull that tool out of a heat shrink holder on the machine in general? I think it was, but I would need to run at a much lower speed. I think, I forget what I figured. Again, I don't want to refer to any numbers because I feel like my memory's not too well. So, but let's just say it was 5,000 RPM. If I tried to max out the machine's power on a 1/2 inch 3-flute end mill at 5,000 RPM or 4,000 or something lower like that, if I tried to do like the material removal rates that I do at 15,000 RPM, yes, I think it's likely that I'd be able to pull that tool out, because in order to hit that same max power, I need a lot more torque. And remember that torque on the cutting tool, having more of that means that you're translating more axial force into the tool. So think about that. That's part of the reason why I like to run at 15,000 RPM. It also, nicer finishes and stuff like that. But I was talking about roughing operations. All right. I'm sorry. This video has gone on long enough. The machine just stopped. I need to change the cycle, change a part out, start a new cycle. So I'm just gonna leave you with that. I'm sorry I don't have fancy editing and a bunch of time to do all that kind of stuff. Animations to describe the things I'm talking about, that would be really cool, but I don't have time to do it, and I don't have the skill to do it, nor do I want to spend the time learning. So hey, if anyone else wants to do that kind of stuff sometime, maybe hit me up and we can partner up. I don't know. Anyway, that's kind of just my thoughts, a little bit about what I learned. Feel free to comment on YouTube or Instagram or something like that, and let's start a discussion. If you want to talk about some stuff, I'll be happy to answer questions. Anyway, that's the end of this video. So if you like it, all that fun stuff. Everyone says that. Subscribe, whatever, dude. Just peace out.